common analytical technique used in chemistry for determining the concentration of an unknown solution is called titration. And in a titration you have two solutions. Again, one is of an unknown concentration. This is what we're trying to determine. This is referred to as the analyte. And we do this using a solution with a known concentration, which we call a standard solution, and it's also referred to as the titrant. The instrument that we use for a titration is known as a burette. And a burette is an instrument that has graduations on it designed to give you very accurate readings of the volume of liquid that is dispensed. So a graduated cylinder has a fair number of markings on it, and that's the main instrument that we use for measuring liquid volume. But the dispensing from a graduated cylinder is by pouring. With a burette, you have this assembly at the bottom that allows you to very precisely control the flow of the titrant coming out of the burette, but also get a very accurate reading of just how much is dispensed. If you notice on the body of the burette, the volume markings, the scale is reversed with 0 at the top and 50 at the bottom. This is so that you can start your titration presumably with the meniscus at 0, and as you dispense, it will give you the actual volume that has been dispensed, eliminating the need to do any subtraction. The scale is reversed from what you would see on a graduated cylinder. The titrant comes out from the tip, and again that control mechanism is referred to as the stopcock. By turning it so that the handle on the stopcock is parallel to the tip and the body, that is the open position. If you turn the stopcock handle so that it is perpendicular to the body and the tip, that is the off position. Now, in carrying out the titration, the first thing that you want to do is condition the burette. And by conditioning, what we mean is use a little bit of the titrant, the standard solution, and you, if you will, prime the inside of the burette. You put a few milliliters inside, turn the burette on its side without pouring any of the titrant out, and kind of rotate the burette so that you are coating the inner walls with that titrant. And then you would dispose of those few milliliters. And then you would fill the burette up past the 0 mark with your titrant, with your standard solution. And then gradually bring that meniscus down to the 0 mark by carefully opening the stopcock and allowing a little bit out. So there your burette will be prepared. Then to get your analyte ready, you have a small amount of your analyte that you're analyzing, and either a beaker or an Erlenmeyer flask. Really, Erlenmeyer flasks are better suited for titrations because it's easier to mix and swirl in the triangular shaped flask of the Erlenmeyer as opposed to the beaker, and there's less chance of spilling. But to this measured quantity of your analyte, you add a small amount of an indicator solution. Might be phenolphthalein, might be bromethymol blue, whatever indicator is best suited for the exact reaction that's taking place. And usually you only need a couple of drops. You don't need a large amount of indicator. Once you have your analyte prepared, then you carefully allow some of the titrant to flow into the analyte by opening the stopcock. Usually you go in small increments, add a little bit, stop it, stir. The key with titrations is you want there to be constant agitation. You want to be constantly swirling so that you can detect exactly when you've hit the end point. And you know you've hit the end point when you see a color change that is based on whichever indicator you happen to be using, but that color change persists. When you're getting close to the end point, the color will change and then it will fade away as the reaction takes place between the titrant and the analyte. But when you've truly reached that end point, you will see that color change persist. And in most cases you want just a slight color change, not a major switch over in colors. For instance, when we're dealing with phenolphthalein, phenolphthalein can turn a very bright pink color in basic solution, but generally speaking we consider the end point of a titration with phenolphthalein to be when you have just a slight pink color to the analyte solution. In order to solve a titration calculation, the first step that we need to do is calculate how many moles of our substance in the titrant, the standard solution, were actually dispensed. And the way that we calculate this is by finding the product of the volume of the titrant that was added times its concentration in molarity. Once we know how many moles of the titrant substance were used, we can use the balanced equation for the reaction between the titrant and the analyte to determine how many moles of the analyte were present or were titrated by that titrant. Finally, once we know the moles of analyte that were used, or the substance in the analyte, we can take that quantity in moles and divide it by the volume of the analyte that we started with in order to calculate the concentration of that titrated analyte solution. So in our first example, we see that it takes 23.10 milliliters of a 0.100 molar sodium hydroxide solution to neutralize 15 milliliters of a hydrochloric acid solution of unknown concentration. So the question is, what is that hydrochloric acid concentration? Hydrochloric acid would be our analyte, the titrant would be our standard, which is sodium hydroxide. So we always want to start with writing a balanced equation for the reaction between the titrant and the analyte, which you see here, and that'll come into play more with the second step. The first part of the calculation is to find out how much sodium hydroxide actually was dispensed in that 23.10 milliliters. So to find the moles of sodium hydroxide, you take the concentration times the volume that was added, and because molarity is expressed in moles per liter, the volume unit that we use in the calculation has to be in liters as well. So you need to convert the 23.10 milliliters into liters. And that would give us 0.00231 moles of sodium hydroxide that was actually dispensed. So now we can take that amount and use the ratio that's established in the balanced equation to find how many moles of the analyte, the HCl, were actually neutralized in that titration. And hydrochloric acid and sodium hydroxide are in a 1-to-1 ratio, so in this case it will be 0.00231 moles of hydrogen chloride, hydrochloric acid, that is present in the analyte solution. So now, taking this information along with the fact that the volume was 15 milliliters, we can calculate the concentration of the hydrochloric acid by dividing the two, and we come up with a final concentration of 0.154 molar HCl. In our second example, we see that we have a 0.250 molar solution of calcium hydroxide, and it takes 14.35 milliliters of that solution in order to neutralize 25 milliliters of a hydrobromic acid solution of unknown concentration. And the question again here is, what is the concentration of that hydrobromic acid solution? Our balanced equation shows that our hydrogen bromide to calcium hydroxide is actually in a 2-to-1 ratio, so this will be slightly different than the previous example. However, we start the same way. We need to figure out how much calcium hydroxide was actually dispensed in that 14.35 milliliters. So we start with the concentration and we multiply it by the volume, and we find that 0.00359 moles of calcium hydroxide were dispensed in that quantity. Now we take that amount of calcium hydroxide and we factor in the ratio of hydrogen bromide to calcium hydroxide, and so we end up multiplying our mole amount of calcium hydroxide by that ratio, 2-to-1 ratio in this case, and we find that the calcium hydroxide neutralized 0.00718 moles of hydrogen bromide. Taking that into account, along with the original volume of the analyte, the 25 milliliters, we can now calculate the concentration of the hydrogen bromide, and we find that we had a 0.287 molar solution of hydrogen bromide. In our next example, we see that it takes 34.62 milliliters of a 0.3 molar magnesium hydroxide solution to neutralize a 15 milliliter analyte solution of hydrochloric acid of unknown concentration. And so we're trying to find out what is the concentration of the hydrochloric acid solution that we started with. We write our balanced equation for hydrochloric acid, magnesium hydroxide, the neutralization reaction. And then our first task, as it has been, is to determine how many moles of that titrant were actually dispensed. So we take the concentration of the standard solution times the volume that was dispensed, and we find that that amounts to 0.0104 moles of magnesium hydroxide. Next, we need to take that molar amount and factor in the mole ratio of hydrogen chloride to magnesium hydroxide. In this case, it's a 2-to-1 ratio. So for every 0.0104 moles of magnesium hydroxide that reacted, it reacted with 0.0208 moles of hydrogen chloride. With this amount of hydrogen chloride combined with the 15 milliliters of the original volume of that HCl solution, we can calculate the concentration of our analyte, and we find that it's 1.39 molar HCl.